Okay, hi. For today, we're going to discuss error detection. But before we proceed to error detection, we are to review first what is data communications and what are data communications code. On your slide, data communications are defined or is defined as a network of computers and computer peripherals which is used to transmit or receive information between two or more locations. On your right is an example of a data network or a data communication system. Okay? In a data communication system, the transmit and receive terminals are consisting of computer and computer peripherals. The transmit, the receive, and everything in between is consisting of computers and computer peripherals. Again, data communications. Our data communication system is simply a connection of computers and computer peripherals used to transmit or receive information between two or more locations. Now, in order for these computers and peripherals to communicate with one another, they need to use a common language, and those are your data communications code. Data communications code are used to represent characters and symbols such as letters, digits, and punctuation marks that is used by your data communication system. Okay, so here are some of the most common data communication code. The earliest was Baudot code. Baudot code is a 5-bit character code, which is used by teletype machines or teletype printers. It was developed by Thomas Murray and was named after Emile Baudot. It is also called International Alphabet Number 2. On your right, figure A is an example of the list of the Morse code. So Morse code represents character or symbols by a series of dots, dashes, and spaces. Figure B is the encoder, okay, or the teletype machine which is used to encode your messages using Morse code. The next common data communication code is the ASCII code. Actually, ASCII code is the most common data communication code. It stands for American Standard Code for Information Interchange. So ASCII, American Standard Code for Information Interchange. Okay, but unlike Baudot code, ASCII code uses 7 bits and it does not use a symbol like that, dashes, and spaces, but rather it uses binary numbers to represent characters and symbols. So it is a 7-bit binary code used for encoding characters and symbols and is the most common data communications code. Okay, Baudot is called International Alphabet Number 2, while ASCII code is known as International Alphabet Number 5. On your right is an example or list of the ASCII codes. Okay, however, in this table, the characters and symbols are only represented in decimal, hexadecimal, and octal. But in actual, an ASCII character is represented as a 7-bit binary number. So you need to translate this decimal, hexa, or octal numbers into binary for you to be able to know the ASCII code of a certain character or symbol. So for example, we have character B, for example. Okay? Character B in ASCII is 42 hexa. Okay? So, letter B. In hexa, it is 42 hexa. So, I will just write the hexa equivalent. So, you just look on the ASCII table for character B, and then the hexa equivalent for character B is 42 hexa. Now, how do we translate 42 hexa into its binary equivalent? Okay? So, we know hexadecimal is can be translated into binary as a group of 4 binary numbers. So, let's start with hexadecimal character 2. In binary, 2 is 0, 0, 1, 0. Okay? So, we translated hexadecimal character 2 in binary as 0010. And then, we translate hexadecimal character 4 into binary. But this time, we will only use 3 binary numbers to represent 4 because ASCII code uses 7-bit binary number. If we're going to translate the next hexadecimal character 4 as 4 bits in binary, so sobra na tayo kasi ASCII is just a 7-bit representation. So instead of converting 4 as a 4-bit binary number, we will just translate it as a 3-bit binary number. So 4 is translated as 1, 0, 0. So this is the ASCII code for character B. The ASCII code for character B is 1000010. Okay? So understanding ASCII, just like our example earlier, okay, but correction, B is 42 hexa, so this is 42. Okay, and 42 is 1000010. Again, this is the translation for hexadecimal character 2, and this is the translation or the conversion of the hexadecimal character 4. So this is 4, 2. Okay, in hexa, but in binary, it's 1000010. Okay, it is important to know the arrangement of the ASCII code. In ASCII, okay, the zero order bit is the rightmost binary number. The zero order bit is the rightmost binary number. This is the zero order bit, B0. And the most significant bit is B6. That is the leftmost binary number, B6. This is your least significant bit, B0. The most significant bit is B6. Again, please take note of the arrangement of the ASCII code. Okay, B0 is the rightmost binary number, followed by B1, B2, B3, B4, B5, and the leftmost binary number in your ASCII code is the 6th order bit. Okay, so all in all, ASCII is consisting of 7-bit binary number. Okay, note, in serial transmission, the zero order bit or B0 is transmitted first, followed by B1, B2, B3, and so on. Now, let's proceed to error detection and correction. So, what is the difference between error detection and error correction? Error detection is the ability to detect the presence of errors caused by noise or other impairments during transmission from the transmitter to the receiver. Okay, it is also defined as the process of monitoring the transmitted data and determining if errors have occurred during transmission. While error correction is defined as the additional ability to reconstruct the original error-free data. Okay? And then lastly, error detection is implemented either at the data link layer or the transport layer of the OC data communications model. Now, a little review regarding your open systems interconnection network model using the TCP/IP. Okay, the lowermost layer is the physical layer, and then you have your data link layer, the network layer, the transport layer, and the application layer. Again, this is the TCP/IP model. So this is how computers communicate in a data communication system, layer to layer, yung communication. And it was said before that error detection is implemented either at the data link layer, which is the second layer, or in the transport layer, which is the layer 4 of your TCP/IP model. Okay? So as a review again, what are the functions of the data link layer? The data link layer receives services, of course, from its lower layer, which is the physical layer. And it gives services to its upper layer, which is the network layer. So, some of the functions of the data link layer includes flow control, media access control, MAC addressing or physical addressing, packetizing, and of course, the error control. So, error detection and error correction is under error control. Now, bit errors. So, we have many types of errors. They are called as single bit error, multiple bit error, and some of them uses the term burst error. So, what is the difference, or what are the difference between those types of error? Single bit error is when only one bit in the data has changed from 1 to 0 or 0 to 1. Okay? If you are sending the data 0, 0, 0, 0, 0, 0, 1, 0, okay? And then at the receiver, you received 0, 0, 0, 0, 1, 0, 1, 0. Notice that one bit has changed from 0 to 1, and that is considered as a single bit error. Although the error is only a single bit error, it is very significant. Why? Because in ASCII, if you are using ASCII, okay, you want to send character B, for example, and then one bit has changed from 1 to 0 or 0 to 1. At the receiver, you will receive another character already. Okay, you can either receive character F or character G. Okay, so you can use the ASCII table to check. Okay. Next, burst error means two or more bits in the data have changed. Or burst error means successive bits have changed from 0 to 1 or 1 to 0 from transmitter to your receiver. Again, if this is what the original message looks like, and then at the receiver, this is the received data. Okay, notice that successive zeros, 0, 0 has changed from 0 to 1, and then you also have another 0 that has changed from 0 to 1. So these are considered burst error already. Again, single bit error is when one bit has changed from 1 to 0 or 0 to 1, and then burst error means multiple bit error has changed from 0 to 1 or 1 to 0. Successive bits in error. But they are both significant errors. Now, how do we detect this type of errors, either single bit or burst error? How do we detect these types of error, or how do the system detect these kinds of error? Okay, there are three detection methods. We have the parity checking, we have the cyclic redundancy checking, and then we have the checksum. Okay, so I will discuss parity checking and cyclic redundancy checking, but you do your research regarding checksum. Okay, but first, what is parity checking? Okay, parity checking actually uses the concept of XOR. Okay, in a parity check, a parity bit is added to every data unit so that the total number of ones is even numbered for even parity check or odd numbered for odd parity check. Now, simple parity check can detect single bit errors. Okay, it can also detect burst error, but only if the total number of errors in each data unit is odd numbered. Okay, we will explain that later on as we go. Okay, this is the review of your XOR truth table. So in an XOR, inputs are 2 bits and then you have a 1 bit output. Input is termed as X and Y, and then the output is on the last column. So 0 XOR with 0, the result is 0. 0 XOR with 1 is 1. 1 XOR with 0 is 1. 1 XOR with 1 is 0. Okay, so let us have this as example. Determine the even parity for the binary number 1, 0, 0, 0, 0, 1, 1. Okay, so to determine the even parity, all we need to do is to inspect the given binary number and count the total number of 1. So you count with me. Okay, so in this given binary number, the total number of 1 is 1, 2, and then 3. So the total number of 1s in that given binary number is 3. Okay, now, the condition of the parity should force the total number of 1s to be even numbered. So if we are to determine the condition of the even parity, again, the condition of the parity should force the total number of 1 to be even numbered. Now, since the total number of 1 without the parity is 1, 2, 3, 3 is an odd number, the condition of the parity should be binary 1 instead of binary 0, so that the total number of 1s when counted, including the parity, will be even numbered. Okay, ulit. To determine the even parity, you need to inspect the given binary number and count the total number of 1s. The condition of the parity should force the total number of 1s to be even numbered, including the parity bit. Therefore, the parity bit for this example should be 1. Okay? In reality, XOR was used to determine the parity bit. How? That is by XORing all the number in the given binary string. Okay? The result of the XOR is 1. So let us try XORing the bits in your given binary number. 1 XOR with 0 is 1. Okay? The result of that XOR will be XOR to the next number. 1 XOR with 0 is still 1. 1 XOR with 0 is 1. 1 XOR with 0 is 1. 1 XOR with 1, which is the next binary number, the result will be 0. And then finally, XOR 0 to the next given binary number, so 0 XOR with 1, the result is 1. So this is the result of your XOR, which is also the condition of your even parity check. Okay? Again, there are two ways to determine the even parity check. One is to count the total number of 1s. The total number of 1s should be even numbered, including the parity check. And then next, you can use XOR to determine the condition of the parity. That is just by XORing the bits in the given binary number. Again, 1 XOR with 0, XOR with 0, XOR with 0, XOR with 0, XOR with 1, XOR with 1. The result of that XOR is equal to 1. Okay? Now, after parity checking, the next error detection technique is redundancy checking. There are three redundancy checking techniques that we are going to discuss, and those are vertical redundancy checking, longitudinal or horizontal redundancy checking, and cyclic redundancy checking. But for now, we can only discuss vertical and longitudinal redundancy checking. We will discuss cyclic redundancy checking next meeting. Okay? Vertical redundancy checking and longitudinal redundancy checking also uses the concept of parity. So please do not forget the concept of parity checking. Okay, vertical redundancy checking is also called character parity. That is, a parity bit is added at the end of a character. The parity is determined by XORing the bits in the character VRC can only detect errors if the number of errors in a character is odd number. So let us have an example for vertical redundancy checking. So in here, I have the solution table to determine the VRC. Okay? Determine the VRC or the vertical redundancy check for the ASCII encoded message lockdown. Please take note that I have used uppercase letters because in ASCII, the uppercase letter representation is different from the lowercase letter representation. And then on the instruction, use even parity check. Okay, again, instruction, use the ASCII table to determine the hexa binary equivalent of the characters locked down. Please review hexa to binary conversion and review the XOR truth table. Note again that ASCII code is arranged as B6, B5, B4, B2, B1, B0, or that is the order of your ASCII code. For example, let us say L, uppercase L, in hexa is 4C. To translate 4C, again, C is equivalent to 1100 in binary, and then 4 is equivalent to 100 in binary. So, the ASCII code of L is 1001100. But take note that the rightmost binary number again is the 0 order bit, and the leftmost binary number is the 6th order bit. Okay, all we need to do is to translate all of our ASCII characters L, O, C, K, D, O, W, N. Translate all those ASCII characters from hexa to its binary equivalent and write it on the table as shown, wherein the 0 order bit is on the topmost and then the 6th order bit is on the lowermost part of the table. So that when L is written on the table as an ASCII code 100, that is B61, B50, B40. And then 1100, B3 is 1, B2 is 1, B1 is 0, B0 is 0. It's basically the same ASCII code but is written on a different format. Okay? ASCII code is written in this manner, but on our solution table, the ASCII code is written in this manner. Okay? So now, again, please try to translate character O, C, K, D, W, and N from hexa to binary and check if my answers are correct. Okay? So now, assuming that I have converted or translated the ASCII character into binary correctly, how do we determine the VRC? Again, on the instruction, it is said that we need to use even parity check. Okay, to determine the even parity again, I have given you two methods to do that. One is to simply count the total number of 1, and then the parity check should force the total number of 1 to be even numbered. And then the next one is for you to XOR the bits in the character. The result of the XOR is the parity. Okay, so let us try both methods. Okay, for character L, if we're going to count the number of ones, 1, 2, 3. So for the total number of ones to be even numbered, Okay, the parity or the VRC should be 1. Okay, let us try that for character O. 1, 2, 3, 4, 5. So the VRC again should be 1, so that the total number of ones will be even numbered. Do that for the rest of the characters. Okay. Now, for the last character N, instead of simply counting the number of ones, let us try to use XOR. Okay? 1 XOR with 0 is 1. 1 XOR with 0 is 1. 1 XOR with 1 is 0. 0 XOR with 1 is 1. 1 XOR with 1 is 0. 0 XOR with 0 is 0. Again, the result of XORing the bits in your character is your VRC. Let us check by counting the number of ones if they are the same. If the results will be the same. 1, 2, 3, 4. So the parity should be binary 0. Okay, so that is how you determine the VRC. Again, VRC is a redundancy checking technique wherein a parity bit is added at the end of the character. It depends if even parity check or add parity check will be used. Okay? Next. Okay, let's go to LRC or longitudinal redundancy checking. LRC is called message parity. Recall that VRC is character parity because the parity bit is added at the end of the character. LRC is message parity because the parity bit is added at the end of the message. Now, instead of XORing the bits in a character, in LRC, the parity is determined by XORing the bits in the message. But just like VRC, LRC can only detect errors if the number of errors in a bit position is odd number. Okay, so let us have the same example. Okay, but this time let us determine LRC. Okay, again VRC is adding a parity bit at the end of the character. So these are your VRC results. The one that we did earlier. These are your VRC results. The parity bit is added at the character. Note that in VRC, this parity bit can only be used to detect error in that given character. Okay? So the checking is per character. The detection of error is per character. Okay? The parity bit that you add for a certain character can only be used to determine or to check error for that character alone. Now, this time, the instruction is we need to use add parity check. We need to use add parity check to determine LRC. And LRC is added at the end of the message. That is why the LRC is on the rightmost column. Okay? This time, we need to count the total number of 1 per bit position for the entire message. This is your zero order bit position for the entire message. Okay? We just need to count the total number of ones for the zero order bit. To determine the add parity check, the parity should force the total number of 1 to be odd numbered. Okay, so let us count. 1, 2, 3, 4, 5. So the number of ones is already odd numbered, and since we are using add parity check to determine LRC, the LRC should be binary 0. Okay? The same is true if we're going to use XOR. XOR the bits in all the bit position for the message lockdown. So, let us do that. 0 XOR with 1 is 1. 1 XOR with 1 is 0. 0 XOR with 1 is 1. 1 XOR with 0 is 1. 1 XOR with 1 is 0. 0 XOR with 1 is 1. And then 1 XOR with 0 is 0. As you can see, the result of the XOR, I mean 1 XOR with 0 is 1. As you can see, the result of the XOR is 1. Okay? But the add parity that we have determined earlier is 0. Okay? Why is it different? Okay? When getting the even parity check, the result of the XOR is the parity. But when getting the add parity check, the result of the XOR, okay, the result of the XOR is your even parity check result. So to determine the add parity check result using XOR, you need to get the complement. Okay? Ulit. Okay? By XORing the bits in your entire message, the result of this XOR is 1. But since we are using add parity check, to determine the add parity check, you need to determine the complement of the resulting XOR. So the complement of 1 is 0. So the final answer, okay, in determining the LRC using add parity check will be 0. Again, if even parity check will be used, the result of the XOR will be as is. But if you're going to use add parity check, you need to get the complement of the result of the XOR to determine the add parity check. Okay? So, let us try to determine the LRC for the rest of the bit position. 1, 2, 3, 4, 5, 6. But since we're using add parity check, the LRC should be 1. 1, 2, 3, 4, 5, 6. So the parity should be 1. Okay, do the same for the rest. Okay, so this is the result of your LRC. If you're going to count the number of LRC bits, the LRC bit is also consisting of 7 bits, which is actually equivalent to another ASCII character. Okay, so 110 is 6. This one, 6. And then 0110 is equivalent to 6. So that is 66 hexa. So use the ASCII table to determine what is the character equivalent of 66 hexa. 42 is 6, and then another 42, translation ng binary is also equivalent to 66 hexa. Now, I want you to notice the importance of LRC with regards to VRC. In LRC, no matter how many characters your data is consisting of, the LRC will just be consisting of one ASCII character or just 7 bits. But in VRC, you're going to use VRC, the number of VRC bits is dependent on the number of characters in your message or in your data. If your message is consisting of 100 characters, for example, you will need to send 1 VRC bit per character. So you will need to send 100 bit additional for error detection because 1 character will need 1 VRC. Okay, so 100 character message will need an additional of 100 VRC bits kasi 1 VRC per character. But if you're going to use LRC, okay, even if the message is consisting of 100 characters, okay, the additional bits that you need is just 7 bits because LRC is consisting of 7 bits only and it is just equivalent to 1 ASCII character. Okay, so that alone will give you that LRC is better to use than VRC. Okay, reliability-wise, the reliability of VRC in detecting error is 50%, while the reliability of LRC in detecting error is around 95 to 97%. Okay, so those two reasons are the main reasons why LRC is used most often than VRC. Okay, but a more effective one is to use LRC together with VRC. Okay, so that's all for now. We will be discussing CRC next meeting. Okay, thank you for listening and please review the VRC example. Please review again the LRC example. Please review the XOR truth table. And please review how to convert hexa to binary and binary to hexa. The ASCII table you don't need to memorize, but be familiarized with the ASCII table. The ASCII table is arranged chronologically. Okay? I'm not asking you to memorize the entire ASCII table. What I'm asking you is to have a glance of the ASCII table and get familiarized with the ASCII table because the ASCII table is just arranged chronologically in hexadecimal counting. Okay, so thank you again and see you next meeting.